The recording thing, but thanks again for having me back on the show, I guess. Excuse me. So today I want to talk a little bit about you know, not only where this research started as part of an in pilot, but the kind of follow on and the success that we've had that was initiated under the pilot. The pilot focused on textile-based wearable sensors for virtual health and physical rehabilitation. So I'm not by training a biomedical person. I'm a material scientist. I'm faculty in mechanical engineering and material science, and I've been involved for many years with the Center for Composite Materials, and it's really an interdisciplinary center, the oldest actually at the UD campus, and it's this interdisciplinary collaboration is kind of part of my training, but it was also really exciting to expand this in terms of injuries. I guess I just want to mention at the very beginning. So we started looking at coating of fibers and coating fibers specifically for composite materials, but we started using these as sensors, and particularly we started to realize that these sensors were sensitive to both in-plane strain as well as pressure. And actually, one of the upshots of this coating process is that they're soft to the touch and breathable. So this idea was initiated with a collaboration with Jill Higginson, who's a director of the Institute for Engineering Driven Health. And so we started this collaboration, and we developed the technology, and we've also patented and licensed it. And actually, our collaboration, uh, we just paid the issue fee for one of the patents a couple of days ago. Started with the INBRI program, and then continued under Unidel supported work. This Henswear initiative is something that Jill led, and we had a small pilot, and also Unidel funding through OEIP. And then continuing, as a lot of people encouraged us to move towards commercialization, we engaged at Delaware Division of Small Business and Horn Entrepreneurship, and we received what's called an EDGE grant from the Delaware Department of State, and founded a startup company called MSET Technologies. And that company, the focus isn't only on biomaterials or biomedical applications, but we also received an SBR from the Department of Transportation. I guess we made these novel sensors, but we go from fundamentals to even more fun. Is that it's expanded, receives intellectual neighborhood accelerator program with Layla Barmaki in computer science and Josh Cashback in biomedical. And very recently, in fact, just earlier this week, we were awarded a NSF Partnership for Innovation grant, and with Jill Higginson as a co-PI, and also Sagar Joshi. And kind of coming full circle is that Sagar was a graduate student who worked on the IMBRI program. So just kind of starting from the beginning, I always like to start with this slide because I'm a composites person, and we integrate nanomaterials with fibers. So what you see in the middle is a single fiber that's about the 10th of a diameter of a human hair, where we've integrated nanostructures onto the surface. So it's kind of a fuzzy or a hairy fiber. And we developed this process, which is really the enabling technology of what we're doing today, is that we chemically treat the nanostructures, and then we use an electric field to deposit them onto a fabric. And on the right-hand side, you'll see it actually creates, so what you're looking at is a cross-section, and it actually creates a coating that is almost like a sponge. You see that kind of texture. So it's soft to the touch, it's breathable, and I think it's a scalable technique, and it's something that we could usually only make a few square inches. Now we can make hundreds of yards of the materials. And as I mentioned, my material science background, we're interested in creating composite interfaces that bond to each other, basically making a better glue. But these are also interesting sensors, and I think this, this kind of, I mentioned from structural health monitoring to human health, is that this is a bridge, that's the South Walnut Street Bridge, downtown Wilmington, and actually we use this material to create a sensor that is, excuse me, a sensor that's actually still hanging on this bridge that we're monitoring. You see the train station in the background. And in fact, it's kind of fun thing. It was a collaboration. Civil engineer. I'm not a civil engineer, but we were kicked off the bridge the first day. It's a drawbridge by the tall ship downtown Wilmington. But so I guess, and those are the sensors, and I am safely on land when all of these photos are being taken. But I guess, sort of this translation, and this is where this INBRI program started, is that this kind of structural health to human health, and where can we use this technology and these sensors and apply it in a biomedical application. And I actually happened to read an article in the Philadelphia Inquirer, of all places, about Jill Higginson's smart boot. And basically, it's an instrumented boot that, if you put too much weight on a broken limb, the LED turns red. And but what are the article actually talked about the sensors, and about half of the article and all the challenges they were having with the traditional sensors. And I was like, we need to talk to Jill, because we were working on these very interesting sensors that were enabled by the technology I just mentioned. So the idea behind this was we could take, the kinematics and kinetics, the gait analysis type of research that Jill does, and take it outside of the laboratory. She has a beautiful lab with motion capture and instrumented treadmill, but you can only monitor somebody for a short amount of time. And I think here is interesting, as we had these pressure sensors that had a ultra wide dynamic sensing range. As I mentioned, always touch to tons. On the right-hand side, the video, if you can see it, is actually one of the interns near the beginning, actually walking with the sensor in their shoe. And in the middle, you actually see in my left hand, I'm holding the sensor, and it slips right in between the insole of my shoe. And we can send that wirelessly to your phone or laptop. And on the bridge, we actually, or even send it over the cellular network. And I always say this, it's sort of like a quantitative Fitbit. It not only measures your steps, but the forces that you're walking on. What was initiated under this grant, or the INBRI grant, and continued since, is a lot of human subject testing. That's a photo of Sagar in Jill Higginson's lab on the treadmill. And one of the things was that this sensor is very accurate. And in fact, on the right-hand side, you see, the comparison with the treadmill measurement. And I think one thing that's interesting is that, and actually, there's a little bit more variation as you're walking faster, and it's partly because we're not taking data at nearly the speed of the treadmill. And recently, we also, so we're missing some of those peak forces just because of the rate. But we also have gone on and done a lot of statistical analysis of the sensor, and one of Jill's students, we co-authored a paper very recently reporting these results in footwear. So this is just a little bit of response. So this is where we have two sensors, one in the ball and heel of the foot. That's what you see on the red and blue lines. And on the right-hand side of this graph, what you see is often referred to, for those who work in gait analysis, as the M curve, and that is the response of the treadmill. So you can see that we're very accurate, but we can also measure both the ball and heel force reactions. And this allows us, now we can take it outside of the lab. So on the right-hand side, what you see is walking up and down stairs. This is walking upstairs. And of course, you see that there are different forces acting on different parts of the foot when you're going over different terrain. So this is, I think, kind of an advance. And we advanced this to the point where we could integrate these into compression garments. So it could be something where we sew it on the sleeve, and what you see in the video there. And what's remarkable is that it's extraordinarily sensitive to this measurement. In fact, that's a 3,000% change in electrical resistance. And when the students brought back the data, I said, well, are you sure you didn't multiply it by 100 twice? But this is, it's exciting because it gives you quantitative measure, and it's something, especially during COVID, a lot of people have been interested since in using it for virtual rehabilitation. And it's kind of difficult to measure range of motion on a video camera on a Zoom call, but this could be worn and be a quantitative measure. Of course, we also put it on the knee. In fact, that's what we designed the sensor for. And we see also this remarkably high sensitivity. And it's not only sensitive to these pretty large motions, but it's very sensitive to delicate motions like a finger. On the left-hand side, it's just a graph showing different angle of curvature, but on the right-hand side, one of our undergraduate students flipped it around. We actually 3D printed the hand to put the sensors on so it would be repeatable, but he kind of flipped it around, and where he can control the hand now by wearing the sensors. So that potentially even beyond where you could interact, human machine interaction. And I think our interest is that it could be a paradigm shift in monitoring rehab. On the left-hand side, I believe that's Tom Buchanan's lab. You see a person wearing a lot of sensors and markers for motion capture. But this is something that could be integrated non-invasively into a garment. We collaborated with some faculty in fashion and apparel studies. On the lower right-hand side, what you see also is we miniaturized the data acquisition, so it certainly could be something that you would wear all the time. Of course, it's a somewhat applied research, but really what we do is extract the fundamentals. And I think what's interesting is that, and there's been a number of papers and master's and PhD theses in this area, but understanding what is the mechanism behind this sensing. On the top is the pressure sensor that Sagar developed. On the bottom actually is really an interesting textile problem, is that we have multi-scale interactions from the wavy fiber to the fiber bundle all the way up to the fabric itself. So it's understanding that and then being able to apply it in rehabilitation. And this also extended, as I mentioned, professors Barbaki and Cashback. It's that I actually play a virtual reality fitness game called Supernatural, and I know I can cheat the game, but this is where we were interested in using this for virtual health and being able to validate this. And what you see in the middle is in Professor Cashback's lab, he has what's called a kin arm, which is a robotic type of a system. And we validated that, but also validated it with a virtual reality headset. So we're able to very accurately track the motion under different conditions. In fact, we're working on a paper, a MIT just defended a month ago, and I swear I'm working on these revisions today. We'll get it out this week. But I guess with that is, I could spend another hour talking about all of the work we've done, but I hope to give a high-level overview of really where it all started under the Embry program. I never worked in this area before, but it's been a very rewarding path forward, and collaborations with faculty who aren't material scientists, but I was working with civil engineering faculty, but now expanded to biomechanics and also computer science. So with that, I just want to thank everyone for listening, and of course acknowledge everyone who did the actual work, all the graduate students and postdocs, Sagar, Amit, Colleen, Seda, and Dehan. And Dehan is also currently a postdoc. Sagar is a scientist now at CCM. And is co-PI with Shel Higginson on the new grant. And I mentioned Barbaki and Cashback, and we worked with Wanta and Cow and Adriana Gorea in fashion, and they helped us make some of these. I can't sew to save my life, but of course, all the research funding, and especially starting under INBRI, but continuing with NSF and a number of other sources. So it's been a really interesting path forward, and I'm happy to take questions, and I'm certainly interested in talking to anybody who has ideas on where we could potentially collaborate and move this forward. So with that, thank you again, and I'm happy to take any questions.